So the next speaker is Samuel Ting, which we talk about the alpha magnetic spectrometer and recent result. Please, Sam.
Good morning. Please take a seat. What I would like to do is to give you the latest result of the alpha magnetic spectrometer experiment on the International Space Station. The International Space Station from here to here is 109 meters. From here to here is 80 meters, and therefore the size of a football field. And on there at this moment, there's a particle physics experiment, and that is AMS. There are two kinds of cosmic rays traveling through space. Neutral cosmic rays, light rays, and neutrinos can be measured with satellites and large ground-based and underground experiments. And you will soon hear this incredible ice cube experiment. And then there are charged cosmic rays. The Earth's atmosphere is equivalent to about 10 meters of water. The properties of charged cosmic ray cannot be measured underground. In space, for long duration, which is the purpose of AMS, order of 20 years, to measure directly the original property of charged cosmic rays. On the ground, only the energy of charged cosmic rays and neutral cosmic rays can be studied by summing up the showers. There are very important experiment results from the Pamela experiment, and Professor Giorgio Picozza sent me this data, shows their measurement with a small satellite, but a very good one, on proton, helium, and proton over helium spectra, as well as antiproton to proton ratio, positron fraction, proton flux, and positron flux. AMS is 5 meter by 4 meter by 3 meter, weight 7.5 tons. It is a TeV precision multipurpose spectrometer. Particles and nuclei are defined by their charge and energy, which is equal to momentum. TRD identifies electron and positrons. 9 layers of silicon tracker measure Z and P, electromagnetic calorimeter measure energy of E plus E minus. Time of flight, there are two banks, measure Z and E, magnet measure the sign of the charge, ring image CHerenkov counter measure Z and E. Therefore, Z and P or E are measured independently by many detectors. It is a precision magnetic spectrometer normally used on the ground. We now put it in space station. It is an international collaboration involving many countries, many institutes, and many physicists. By CERN standard, this is a small experiment. And let me mention Professor Roberto Batistone, for many, many years was the deputy PI, and working together, he has made fundamental contributions to the success of AMS. In fact, I would not know what happened to AMS without him. We also have a very large group of national contributions from Italy, and coordinators formerly is Roberto Batistone, now is Professor Bruno Bertucci. I'm glad to see Professor Borgia and Dr. Giovanni Ambrosi are here today. Years ago, Roberto Batistone and his group developed a precision microvertex detector, a silicon detector, with resolution of 8.6 microns for a collider experiment. And this is Professor Batistone showing US Senator Bill Nielsen and the former president of the Italian Space Agency, and Johann Dietrich Müller, now the head of ESA. Transition radiation detector identify positron electron by transition radiation and nuclei by DEDX. It takes a very large group, people from Aachen, from the United States, from Rome, took about 10 years to finish this detector. 9,000 of this detector's proportional tubes were made. Out of 9,000, 5,000 were selected. The longest one is 2 meters in length, is central to 100 microns. In space, for 4 years, we have been able to measure the CO2 leak rate. CO2, as you know, is notorious to keep it tight. This is why Coca-Cola doesn't stay for a long time. On space, we store 50 kilograms of xenon, 5 kilograms of CO2. They measure the CO2 loss. There's no leak, but there's diffusion. It's 0.44 grams per day, and therefore, this is the measurement. It's steady, and so we can be in space station for 31 years. Time of flight counters measure the velocity and charge. Velocity resolution at z equal to 6 is 50 picosecond, basically limited by the electronics. And this is by Professor Ting, Laurenti, Plenary, and Nino Zekiki and Veronica Bindi, and others. Silicon tracker, there are 9 planes with 200,000 channels. The coordinate resolution is 10 microns. A resolution of 10 microns has no meaning unless you know whether the chamber moves or not. The movement of the chamber is monitored by lasers. The outer layer are calibrated with cosmic rays in every 2 minutes. And this is Professor Bruno Bertucci. The chamber is a very difficult job. It's coordinated by Professor Battistone, Bertucci, and Giovanni Ambrosi, and others. Rain image Cherenkov counter was designed under the leadership of Giuliano Laurenti, mostly constructed in Spain and in France. Use the fact a charged particle goes through a radiator, emits Cherenkov cone. The angle of the cone is measurement of velocity. It's measured to accuracy 1 part in 1,000. The intensity measure nuclear charge. And this is a measurement of aluminum and 9 TeV. And this is a section of the Cherenkov counter with 11,000 sensors. For most of the detector, 2 are made, 1 testing the ground, 1 for space. Electromagnetic calorimeter followed the fundamental development of Franco Civelli with the participation of the French group and the Chinese Space Agency. There are 50,000 fibers, 1 millimeter in diameter, distributed uniformly inside 600 kilograms of lead. You provide a precision, 3-dimensional, 17 radiation length measurement of direction and energy of electron positron to TeV. How do you separate protons from electrons? The proton rejection is done in 2 ways. 1, you measure the momentum with the tracker, and 2, you measure the energy of equal, and if it's an electron, P must equal to E. In addition, you measure the shower, and you measure the pulsar distribution. And together, you reach, for the TRD alone, you reach a rejection order of 10 to the 4. The total rejection is larger than 10 to the 6. Before we send to space, we calibrate the detector extensively at the CERN accelerator. So we use protons, positrons, electrons, pion. Pion is to simulate proton more than 1 TeV. Since cosmic ray goes in all directions, but accelerator beam is going in one direction. And so we have a movement detector move to 2,000 positions to simulate exactly the response of the detector to electrons and to protons. Electronics is a major responsibility of Taiwan and MIT. To have a precision electronics in space. To get one board working in orbit, we need to make 10 boards on the ground. In total in space, there are 464 boards on orbit of 70 different types. This is Roberto, who spent a lot of time to get this in space, and this is the day we launched the detector in space. In 4 years on the space station, we have collected more than 65 billion cosmic rays, but collected very precisely. To match the statistics, systematic error study have become very important. Because it is a very precise detector, so data was analyzed by at least 2 independent international teams. And there's Mr. Schutko, Mr. Cooney, Matteo Duranti, and very important Bruno Bertucci, many others. Let me share with you first the physics of 11 million positron-electron events. To measure positron-electron from hadrons, you do transition radiation and shows the transition radiation spectrum of electron and proton. Therefore, by making a cut, you can select electrons from proton. You match the energy from ECOL and tracker momentum requiring E equal to P for electron positron. For protons, P is larger than E, as shown in here. It's always good to have a spare. So this is electromagnetic shower distribution, separate protons from electrons. One of the things we're very interested in to study the origin of dark matter. Has been said before, most of the matter in the universe is not visible, and therefore it's called dark matter. Collision of ordinary cosmic rays produce positrons and antiprotons, and therefore if you plot positron to electron-positron ratio, you expect a curve like this. And the curve is decreasing because number of positrons and nuclei decreases with energy. But collision of dark matter, such as neutrino, will produce additional positrons. And the characteristics of this curve, it depends on the mass of neutrino. Similarly, for antiprotons. To identify dark matter signal, we need first to measure positron, electron, antiproton accurately. And then you need to understand the background. So you need to measure the precise knowledge of cosmic ray flux and also propagation and acceleration of nuclei. So this is the measurement of MSO2 based on 11 million positron electron events. This is the positron fraction as function of energy. The first thing you do is to do a verification with 2 independent samples. And so most of the events we use pass through TRD and ECOL. Because TRD is very precise, so you can select the events with TRD alone. And this is the measure positron fraction with TRD alone, and compare with the events we use, and they are exactly the same to a percent level. That means the event we used is correct. So this is the measured positron fraction. It goes up and then gradually flatten out. For comparison, this is a Fermi measurement, this is Pamela measurement, and many other measurements. So with this spectrum, you can study its detailed behavior. You can measure the slope, how the spectrum changes. And the slope gradually increases, flattens out, then drops to zero. The slope reaches zero means you have reached the maximum. At this moment, this is our measurement. And this is a prediction based on neutrino has a mass of order TeV. There are many, many explanations of our data, and one of them is pulsars. And so far, I think more than 100 explanations. And people have asked me which one is correct. My answer is they're all correct. Makes no difference. Our responsibility is to measure this accurately. And this is the prediction of pulsars. Even though our maximum is in here, where pulsar, the maximum is here for such an important thing, of course, we need to measure this very accurately. And so in the next few years, we should be able to produce such a curve. If it's from dark matter, it will drop very sharply, very quickly. If it's from other cosmic astrophysical sources, it will drop slowly. I think if it drops very, very quickly, it will be difficult to explain by any other ways. This is our measurement. This is the measurement of electron flux from 1 GeV to a few hundred TeV before AMS from many experiments. This is the AMS measurement to an accuracy order 1%. 1% measurement is quite difficult even in accelerators. We're being able to do that mainly because we calibrate the detector and have multi-redundant measurement of electron and positrons. This is the measurement of the electron flux multiplied by e⁻³ just for display purpose, because people assume the spectrum goes as e⁻³. And this is our measurement compared with other measurements. Similarly, this is our measurement of positron flux. The flux goes up, flattens out, goes up again, multiplied by e⁻³. And this is the measurement extended to higher energy range. So this is the summary of electron flux and positron flux. For electron, it's in this y-axis. For positron, it's in this y-axis. If you do the spectral index, phi equal to E gamma, and this is the spectral index for positron, the spectral index for electron. So you can make the following three observations. The first, the electron flux and positron flux are different in magnitude and energy dependence. Both spectra cannot be explained by a single power law of e⁻³. The spectra of positron and electron are not the same, they're quite different. Both change their behavior at 30 GeV. An important observation is the rise in positron flux. Positron fraction from 20 GeV is due to the excess of positron, not the loss of the electron, and because the positron flux is harder. And this is the result of E plus E minus done by AMS and compare with the previous measurement. There were many measurements, and you can read many of them in newspapers showing discoveries, but our results do not reproduce any of the previous results. In fact, the results we have measured so far have not been able to reproduce any of the previous measurements. For the electron-positron flux cannot fit to a single power law, the sum of the electron-positron fit extremely well with a single power law with gamma equal to -3 plus rather small errors. A very strange observation. We also measured antiproton to proton This result is not yet finished, but is very, very close to finished. For antiproton to proton ratio as function of its kinetic energy. And this is the comparison with the previous measurement, and this is our spectrum. Tends to be flat. The spectrum does not fit the theoretical prediction based on pre-AMS knowledge of cosmic ray collisions. And either this has to be changed or there's something new here. So now we have measured this spectrum. We will take some more years to measure the drop-off. And then the question is, what is the background? To understand the background, we need to know the flux and know the propagation. So to know the propagation, we need to measure the spectrum very accurately. There are 7 independent ways to measure nuclear charge. From the tracker, from TRD, from time of flight, from the inner tracker, from lower time of flight, and so forth. For z equal to 6, the most accurate way is to use the inner tracker with a very accurate result to identify nuclear charge. So this is our measurement of periodic table. 2 of the 7 measurements. Number of events, a function of charge. Because it's on log scale, you could not see, we actually now measure to z equal to 50. It's basically limited by events. If you look the lower element in the periodic table, you normalize it, and you will see a curve like this. And this shows the overlap is order of 1 part in 1,000. So it's a very accurate measurement of these things. So this is our last paper on precision measurement of proton flux. Proton flux has been measured over half a century. And our measurement is from 1 GeV to 1.8 TeV. To match the statistics of 300 million events, extensive systematic error study has been made. This is the rigidity range. This is the measured phi, statistical error, and this is error, systematic error due to trigger efficiency. This is systematic error due to acceptance, namely acceptance and event selection, background contamination, geomagnetic cutoff. This is due to unfolding, namely matching resolution with beam width and momentum resolution function. And then this one is the absolute energy scale. So this is the measured proton flux, and the flux based on 300 million events in the rigidity from 1 to a little bit more than close to 2 TeV. So it's multiplied by R2.7. The flux goes down, then changes behavior. Therefore, it does not fit to a single power law. But it changes very slowly, smoothly, no sharp structure. This is the comparison of our measurement with the previous measurement. Previously, people have seen sharp structure and ore goes up, and these are not reproduced by us. We, of course, have calibrated detector before sent to space at very high energies. So the proton flux, where it does not fit to single power law, it does fit to two power laws. One is R gamma, another is gamma plus delta gamma, with a characteristic transition function R0 and smooth function S. And you see the fit is with very good chi-square, and this is the fit if you only use a single power law. Obviously, it shows it fits to 2 power laws. With 300 million events, you can make independent measurement of the spectral index by using gamma d log phi, d log r. And you see the spectral index is not minus 2.7, but it goes down, then it gradually goes up. You actually have a structure. This is our helium flux, which will be published sometime next week. And this is based on 50 million events. The structure goes up, can flatten out, goes up again. Again, cannot be fit by a single power law. This is a comparison of our helium flux with other measurements. It does not reproduce any of the previous measurements. Particularly, we don't see any structures. You can fit the helium flux again with a two-power law, and it fits very well with two-power law. Does not fit at all with a single power law. With 50 million events, you can measure also the spectral index function for helium and compare with proton. What you see in here is the magnitude are not the same, not 2.7, but the functional dependence seems to be very similar. This is our measurement of lithium flux. Lithium is supposed to be secondary, and therefore the flux should fit to a single power law. Not at all. We don't see a single power law. And this is compared with the previous measurement. This is an important measurement to understand propagations. And if you fit the lithium flux with two-power law, and you will see it fits quite well with two-power law, does not fit to a single power law. So if you summarize together for proton flux, for helium flux, for lithium flux, you will notice the slope change at about the same rigidity for proton, helium, and lithium. I simply do not know why it is this way, and nobody seems to know why it for lithium also a two-power law. This new observation contradicts the current understanding of cosmic ray behavior. So the latest AMS measurement of positron fraction, antiproton-proton ratio, the behavior of flux as function of electron, positron, proton, helium, and other nuclei provides a precise and unexpected information. The accuracy and characteristic of the data simultaneously for many different types of cosmic ray require a comprehensive model to ascertain if the origins from dark matter, from astrophysics sources, from acceleration mechanism, or combination. Our responsibility is to provide the most accurate data across the periodic table and leave the exciting explanation to distinguished theorists. Let me make one comment. We do not know we see dark matter or not, but all our measurement of positron fraction so far shows no contradiction. This, of course, does not prove you have seen dark matter, but only after a few more years, when we finish measurement of the sharp dropout, we will know better. Thank you.
Thank you, Sam. Thank you, Sam, for this very extensive talk. Time for one or two questions. One there.
This proton data implies some excess around the TV.
Yes. What is the definition of access?
Means the more proton as we expect. The proton comes from something we don't know. Beyond or around 1 TV.
Yes. I don't know this. This is a measurement for to say the axis, you have to assume a theory. And I don't assume
means what we
theory.
expect, like the first power law, okay, let's suppose it's a diffusion background. And then you have somehow more proton what we expect. This is what I mean by XX.
Let me make the following comment. Take Roberto, Bruna, myself, and many others, 20 years to build a spectrometer. And I think in the next 20 to 30 years, nobody is foolish enough to put another magnetic spectrometer in space. So our first responsibility is to do this correctly. So this data is correct. That's the only thing I can say. How to interpret that, okay, I leave to the work of theorists.
Okay, there are two questions there, 1 and 2, and then we close this
First one.
talk there.
This is not a question, it's a comment. I admire the precision of this result, and I appreciate the fact that you stress that in the interpretation, it's very important to understand the propagation of cosmic rays. But I want to stress also that it is very important to understand where are the sources of cosmic rays in the galaxy. And in particular, standard models of propagation make an implicit assumption that the sources are distributed with axial symmetry, sort of uniformly in the galaxy. Whereas we know that if the sources are supernova, then they are concentrated in spiral arms, and there is very complicated motion of the spiral arms relative to the Earth and the Sun, and this has not been taken into account systematically in most of the propagation calculation. So it is not just the propagation that should be taken into account, but also the location and the source. And when you put these two things together, some of the excesses that you describe, in particular the positron excess, disappears. There is no excess relative to a standard model if you take into account the fact the sources are not distributed uniformly.
This is a very important remark. I have not clearly not mentioned all our results. Okay. Let me just mention, we measured the isotropy for protons, it was done, I think, in Milano, and for positrons to electron. And anisotropy is limited less than 0.3%. 0.3%. Okay. Now, there are many models. Right? One of them is you mentioned. And for that model, you require a special B over C. And the B over C should go down and flat. And our measurement, which I didn't show, our measurement of B over C does not agree with the model. Our measurement of B over C goes down rather steeply, and the model requires flattened B over C. So I think you're absolutely right. Once we have all the measurements, we will make a tighter constraint of all the models.
Okay, thank you. Last question. Unfortunately, we have no time for more questions.
Hello. Working? Yeah, two questions. Could you tell us the formal schedule for the submission of your paper of the anti-proton flux? And the second, in principle, you have already reported the fitting of the diffusion coefficients, energy dependence, small delta, right? Delta should be from 1/3 to 1/2 or something. So in principle, you could plot the background level of the antiprotons, but will you show us the background level, formal background level, by fitting by your group?
Well, Mr. President, you have to interpret what was the question.
The first question was easy to ask to understand. It was about the submission time for the paper on antiprotons. The second one, unfortunately, was not clearly understood.
Antiproton, I have told my collaborators, we publish the paper as late as possible
Okay, and
because
second
we
one,
have no competition.
second
All
one,
responsible. Let me finish. We always have 2 or 3 groups, international groups, analyze the same data. And when all 3 groups agree within 1%, we publish the data.
I think the second question was about using the data to calculate the background to the antiproton, if I understood correctly.
yeah,
your
by
question.
using your formal, the diffusion coefficient, the energy dependence, small delta. Small delta is one side.
We have 65 billion events, and we're always behind in analysis because analysis takes time. Processing 65 billion events takes enormous amount of time because there's 300,000 channel signals. So we have many things not analyzed, and so we unfortunately have no time to look into theoretical implications. So we have decided to publish the data very slowly, like the proton. This will be the only publication, I think, in the next 10 years or 20 years. There will be no other publication
Yeah, I
of
agree.
protons because I don't think we can do better. For helium, there is a chance we use TRD, go to much higher rigidity. But so we have not looked into theoretical implication, but I think we had a 3-day meeting at CERN, and many theorists were interested, and we try to provide the data to the theorists, let them interpret it for us. Mainly we just buried under enormous amount of data.
Thank you so much, Sam, and thank you again for this presentation.